Alright, so we're going to start talking about measurement and data processing. So what this is going to let us do is execute laboratory experiments with a higher degree of accuracy and precision, and also let us know if our results are valid or invalid. I'm going to let you know right now that this is incredibly boring. This whole unit's boring and very, very dry. So, sorry. Suck it up. So there are two parts of measurement and data processing that we're going to briefly go over in this PowerPoint, and then I'll go into more detail in class. Those two parts are going to be uncertainty and error in measurement and results. So we're going to talk a little bit how that error is found in the measurement and how that error propagates into the results and how we can figure that out. And then we're also going to look at graphical techniques just a little bit as well, and how to scientifically explain the relationships between the independent and dependent variables. Is it proportional, inversely proportional, quadratic, inversely quadratic, anything like that? We're going to talk about these brief terms. So just to start off, let's start to talk about why we need to talk about this error in data processing. So in practical science, so in labs basically, so when you're actually starting to apply the science, the results of the experiments are never completely reliable because there always are some sort of errors involved and also uncertainties that are based in your measurement tools. So because of that, and then especially in quantitative work, when we're starting to work with numbers, to be able to figure out how much error there is, to be able to assess the magnitude of these and their effects, it starts to give us a sense of reliability of the final result. How correct is our answer? How do we know? And where does it fall within the range of error? It's important for us to differentiate between two terms here. The first one is going to be accuracy, and then also we need to talk about precision as well. These are going to be two very key terms. We're going to talk about that immediately here. So if we're looking at three targets, we're going to talk about these in terms of precision and accuracy. And I'm going to give you a quick example here. The closer you are to the actual target, so here, when we're aiming for the center point, we are looking for accuracy. A-C-C-U-R-A-C-Y. Accuracy is when we're aiming for a center target. So this is very accurate. It hit the target we were aiming for. This is inaccurate. And down here, all four of these are inaccurate as well, because none of them hit that point. Precision. This is just a way of describing how well were you able to repeat your results. So basically, if you have data points, are they clustered in the same area? So this has a degree of high precision, because all of our points are clustered in a certain area. This also has high precision, because these are clustered in an area. So notice that precision has nothing to do with accuracy, and these have very low precision. Our data points are all over the place. They never agree with each other. They are completely spread out. So two different terms. Accuracy is how close you are to the target, and precision is how repeatable was your experiment. So our final definitions are going to be these. The accuracy of the result is a measure of how close the result is to an accepted or literature value. So if we were boiling water, we would compare our results to the accepted value, which is 100 degrees Celsius. So if we're looking to figure out what our, like, how accurate we are, we would compare our value to 100 degrees Celsius and see from there. We have a nice little equation for this, the percent deviation, which is basically your value minus the accepted value divided by the accepted value. So this is going to just tell you how close were you to the accepted value, one way or another. Accuracy is a measure of systematic error. So if an experiment is accurate, then systematic error is very small. So I'll get into systematic error later on, but just remember accuracy has to do with systematic error. Precision. Precision is a measure of how close the repetitions will be to each other, so you need to be thinking about, on our little target there, if we have dots clustered all in the same area, that's high precision. Precision and accuracy are exclusive. They are two different things. Precision or reliability of an experiment is the measure of random error. So if the precision is high, then the random error is small. So then we need to talk about this. So what is the difference between systematic and random? Random uncertainties or random errors, these are mostly going to come from instruments, so limitation in the instrument. So if I'm using instruments that are subpar, they're not as accurate, so you should be thinking like our analytical balance, which goes to 3 decimal places, or a triple beam balance, where you have to move the weights and just wait for it to balance out perfectly. One of those is better than the other, and then that's going to have to do with random error. And then this is also has to do with the way a measurement is made. So if you're looking at the meniscus or not. Random errors make a measurement less precise, but not in any particular direction. So that's why we use these as a plus minus thing. So this could be any number from 44.25 or 44.15. Really what it's saying is we are plus or minus a whole number to the left. To the right, sorry, it's been a while. So this could be 44.25 or 44.15. And this uncertainty value is just going to come from your instrument that you're using and how you can tell. So if we were looking at the burette to the right, so first off, notice that these are inverted. So what we have here is 43, and then we could just count down. So 43.1, 0.2, 0.3, 0.4, 5, 6. So then if we were reading this, we would say that this is about 43.6, whatever it is, decimeters cubed, centimeters cubed, whatever value that this is. It's unitless right now. But since we're only going to give this, if this is all the information we know that we're saying that this line is closer to 43.6 than it is to 43.5 or 43.7. So we're saying it's closest to this line. But we're not giving an estimate about how close it is. And if you're not going to give that estimate, what you need to do is you need to say 43.6 plus or minus 0.05, because this could be 43.55 or 43.65. Either way, what it's saying is that it's closest to this number with a margin of error, a window where you could have been right or wrong. So let me erase this and get this out of your way. If we're reading a digital instrument, so our balances, for example, it's going to be half the last digit. So, and then you're going to go 1 decimal place past. So, for example, if this is what our analytical scale is reading, and I see I have 1, 2, 3 numbers behind the decimal place, it's going to be 3 zeros and then a 5. that's going to be our way of determining the margin of error. So you're going to go past the decimal place, plus or minus 0.5. Alright, so let's keep on going. Large random uncertainties obviously decrease precision of the values obtained and can lead to inconsistent results if the procedure is repeated. So basically, same idea as precision goes with random uncertainties. So the more precise you are, the smaller your random uncertainties are. If only one reading is taken, and this is a really good lesson for science in general, then a large random uncertainty can lead to an inaccurate result. For example, if I do the water boiling and I get through some sort of random error, I find that the boiling point of water is 73 degrees Celsius. If I only have one data point, that's a completely inaccurate result only because of random uncertainty. Always, always, always have more than one. One data point is never enough. Also, you should just start to prescribe to the life lesson that you always need more data. The more data you have, the more conclusive a result can be, the more firm you can stand behind that result, the more reliable the result is. Repeating experimental determination should, however, increase the precision of the final result as the random variation should statistically cancel out. So remember how we said that, I'm going to use this example up here again. So if I got 95 degrees Celsius, but my random error said that I should have plus or minus 10 degrees. It's a really bad, it's a huge window for error. Eventually, this random error, since it's plus or minus, it'll eventually cancel out. So I'll have a series of things where it's going to be 92, and then 97, and 98, and then 93, 85, 102, 88, and 105. All of these, because even though they have a huge range of values behind them, all of these random errors will eventually cancel out. They'll end up averaging out to being 95. So if you added all those up and divided by, what does that end up being? 8, you'll end up with 95 as your answer. So keep that in mind. Repeating, getting more data is going to cancel out any random errors, but systematic is a little different. Systematic errors are due to identifiable causes. So this is something that I can point at and be like, this is the reason why. Whereas random errors, it's just kind of like, well, my instruments weren't exactly as accurate as I was hoping for, but this would be something like, my instrument wasn't correctly calibrated. So my instrument wasn't set up and prepared correctly. That's something that you caused. It's identifiable because I forgot to calibrate my pH meter, so therefore my pH meter is going to be wrong. I was reading from the top of the meniscus rather than the bottom, which is going to change all of my values from there on out. So this is something that I can point to and be like, oh, this is why this happened. Systematic errors are things that need to be stated 100% of the time. Random errors need to be addressed. If you ever come across a systematic error, you have to figure out what it was. Systematic errors always affect a result in a particular direction, unlike random errors. So for example, if I have a graph, and if I have a systematic error, my graph is going to either be skewed up or it could be skewed down. But what you'll see is a full shift. It's going to result in a particular direction. So always larger values or always smaller values. It's not going to be random. This one was larger and this one was smaller because that is a random error. Keep that in mind. Random uncertainties can be reduced by repeating readings. Systematic errors cannot be reduced by repeating readings. So systematic errors cannot be diminished just by repeating the results over and over and over again, whereas random can, because as you're trying to eliminate random, you're really just trying to get rid of the noise in the data. And I'll talk about what that means, the noise as well. So just remember that as for future reference. So uncertainties in calculated results, significant figures. This is what this is all about. Significant figures. You're going to hear me call these sig figs. There's a few rules here. First off, all non-zero numbers count. So I'm seeing 1, 2, 3 non-zero numbers. So this is 3 sig figs. 1, 2, 3, 4, 5, 6. So this has 6 sig figs. Zeros that are located between non-zero digits are significant. You will hear me call these sandwich zeros because they're sandwiched in between two non-zero numbers. So since these two are in between two numbers, 4 sig figs. Since this is stuck in between, this 1 0 is stuck between the 6 and a 2, that's 3 sig figs. These all count. Trailing zeros have a really tricky rule to them. So basically, they're only significant if their number contains a decimal point. Otherwise, they don't count. So what I'm seeing here is this is my trailing zero. So the 0 is at the very end of the number. And it also has a decimal point. So it counts. So this has 1, 2, 3, 4 sig figs. On my next number here, I have no decimal point. So these zeros effectively don't matter. So I really only have 1, 2 sig figs. And that's where this 2 is coming from. This is going to be the rule that trips you up all the time. Another example, something to be on the lookout for. If I have 120 and 120 with a decimal, these are two different numbers. This has 2 sig figs. This has 3 sig figs. I will explain to you why this is the case in person. It's not going to do me a lot of good to explain it over this because you're just going to have questions anyways. And then zeros to the left of the first non-zero digit are insignificant. They don't count. They're just placeholders. So none of these zeros really matter. 3 sig figs. Doesn't matter. All of these are junk. They don't do anything. They're just there as a placeholder. We could write this in scientific notation and get rid of them. So that's why they don't matter. Oh, rules for math and sig figs. So the idea behind this is your calculated value, the value that you do math to figure out, cannot be more accurate than the numbers that you got from your measurements. Meaning your empirical data that you collect is going to be the baseline for what your answer can be. So if we're doing addition and subtraction, and these are 3 different measurements I have, they have different numbers of digits past the decimal place, and that's what's most important. So least amount of sig figs behind decimal is going to win. So what I'm seeing here is I have a number with only one number behind the decimal, sorry, 1 digit behind the decimal place. So my answer can only have 1 digit behind the decimal place. So I add the numbers up like normal, and then I round to figure out what it is. So I know I should only have one number, so I round the one before it. 9 goes up to a 10, so this 2 changes to a 3, 25.3. Multiplication and divisions, it's actually a little bit easier. You're just going to count up how many sig figs there are total in each number. So what I'm seeing here is I have 3 sig figs and 4 sig figs. And your answer matches the number with least sig figs. So I've got 3 sig figs here. My answer needs to have 3 sig figs. So I do the problem like normal. I'm sorry, I guess this has 4 sig figs. I missed that number. I do the problem like normal. I get out my answer, and then I round it to 4 sig figs. So I count left to right, 3 sig figs, because that's my smallest one. 1, 2, 3, and then I round this number. The 3 rounds down, so I keep this the way it is, 230. Don't put the decimal place. Or, I'm sorry, you do need the decimal place, because you need to tell me that this 0 matters. So when you would write this, you would write it as 230 with a decimal place. Because remember, if you wrote it like this, that's only got 2 sig figs. It's not correct. This has 3, which matches the 3 that we needed before. I know it's kind of a lot of rules, but it's the way it goes. I don't know how to put it any other way. So when you're doing combined addition and subtraction and multiplication and division, basically you're going to first apply the rules for the addition and subtraction. So determine the number of sig figs for that step, and then you're going to apply the rules for multiplication and division. So addition and subtraction first, and then multiplication and division next. Absolute and percent uncertainties. The absolute uncertainty is the number that you would give me, this plus or minus by. So that's so in this case, my absolute uncertainty is 0.05, plus or minus 0.05, whatever that is. And then the percentage is when you're just going to take the absolute, and you're going to turn it into a percent based off the value, the measured value. And you can see that right here. So they're taking the uncertainty, the absolute, and they're dividing it by the measurement. And then they're going to multiply it by 100, just to make it a percentage. And that's going to end up giving us this plus or minus 0.18%. So then we would just write this if we wanted to. We could say 28.5 plus or minus 0.18%. For the most part, when you're writing this out, it's not going to be accepted. You're going to want to give me the absolute uncertainty, but the percent uncertainty is going to be good when you're adding in error bars to a graph. Uncertainties in individual measurements can be combined to calculate the uncertainty in the final value of the quantity being determined. In other words, if you're doing addition and subtraction, you're going to add absolute uncertainties, and multiplication, division, and powers, so like x squared, you're going to be adding percentage uncertainties. If one uncertainty is much larger than the others, ignore the other uncertainties and estimate the uncertainty based on the larger one using the rules listed above. So for example, if I'm going to do this one, and I've got 28.1 plus or minus 0.05, and I'm going to add that to 17.9 plus or minus 15.0. This uncertainty is so much bigger than the other one, you can ignore it. This is going to lead to 100 questions about, okay, well, when do I know it's big enough to ignore, and how can I justify that? And these are all going to be things that we're going to just discuss about in class on Friday. We're going to be missing a lot of people on Friday because of the Munich trip and Project Centipede, but we're going to go pretty slow through this unit just because we've got ourselves some time and we need to do a couple experiments to practice this out anyway. So feel free to ask a ton of questions, and I'm leaving this as just the surface level. Okay, so now this is just going to be an example problem. Remember that when you are doing, you go addition and subtraction first, then multiply, divide. And remember that when you're doing addition and subtraction, give me 1 second. You're doing absolute uncertainties, and then if you're doing multiplication and dividing, you're doing percentage uncertainty. So I'm going to set this up to start, and then I'll show you how it works through on the next slide. I do mine a little bit different. There's 2 different ways to do it. It doesn't really matter. You'll get the same answer either way. So I'm going to just set it up with only the values to begin with. So I'm going to do 123 times 12.7 minus 4.3. And then I'm going to run a corresponding problem off to the side here. So what I'm going to do then is I'm going to take my 0.2 and I'm just going to add it. These numbers correlate with the uncertainty here. So what ends up happening is I should end up getting, what is that, 8.4 plus or minus 0.3 for this little area here. And I'm going to be multiplying this number with 123 plus or minus 0.5. And now what we need to do is, since we're multiplying now, we need to switch this to percent uncertainty. We need to do these into a percentage. I'm going to just jump to the next slide where you can start to see this worked out in text form. And then we're going to be doing these practice problems kind of a lot, so you'll have tons of time to ask me questions. So then to work out this problem, you'll start to see a lot of the similar stuff. What I did in this situation on here is I've just done the problem, the math problem, so this would be my answer without dealing with any of the uncertainties this time around. And then you can see this happening again like I did before. The B minus C is when you're just going to add up those uncertainties for B and C to get 0.3 plus or minus 0.3. And then the percentage uncertainty, since we're going to start to multiply, is when you're going to take this, there was, remember, 0.5 plus or minus. That was the uncertainty for A. And then we just divided it by the whole measurement, and we ended up with this. And I'm going to just do the same exact thing now, but with the percentage uncertainty of B minus C. And there's that 8.4 number I got, because remember I had at one point on the previous slide 8.4 plus or minus 0.3. And then this is me just calculating out the percentage uncertainty for that area. When you are doing multiplication and division with your percentage uncertainties, you just add the percentages. So then you can see my 0.47 and my 3.571 percentage uncertainty. And then I'm going to use this. This is the percentage uncertainty in X. And remember, X equals this number. And from that, I can find out the actual uncertainty. I can do 103.3.2 times my percentage uncertainty, 3.978%, which remember, that's really just divided by 100. and that'll give me my actual uncertainty. So in this case, 41.1. So therefore, x ends up being that value plus or minus 41.1. This is an incredibly precise number. Our values to start with weren't this precise, so our answer can't be this precise. So what we need to do then is use our sig figs to round it out. So remember, this is a multiplication problem, so I'm going to end up picking the number that has the fewest sig figs there. So my first number should have only 2 sig figs in it, and then we normally round the uncertainty so that there's only one significant figure. So give the uncertainty to one significant figure. So then my final result would be 1030 plus or minus 40. I'm sorry. I end up with 3 significant figures here. So 1030 plus or minus 40. Okay, so graphing techniques, I'm going to go really quick through this. Graphs you're going to use them a lot. They're incredibly useful. So you just need to kind of see a couple of results. So this is an example of direct proportionality. This is just a basic linear relationship. So technically this would also be linear, but because this is positive, we say it's direct proportionality. This is going to be a negative slope because it's going down. So we just call it a linear relationship. You could call this a positive correlation if you wanted, or you could call this a negative correlation. So y has a negative correlation to x. Next up is we can see inverse proportionality. Notice that whenever you're having these proportionalities, they're starting through the origin. That's pretty important too. And then we can also have an inverse linear relationship, and it's not starting in the origin. If we took this, since it's inverse, we changed our x-axis to 1 over that value. If we took this graph and we plotted it as a normal x value, you would see it behave more like this, like a typical 1 divided by x. So these are technically the same graph. We've just shown the way that our x-axis is going to be marked in different ways. So keep that in mind. There's many different ways to show a graph. We're still going to get into log graphs and all sorts of fun stuff. So I know it's going to be riveting. And then just a couple of rules for this. When you're drawing graphs, choose axes that are set up so that the graph can take up as much of the room as possible. So for example, if I have a graph that goes like this, cut it. Cut it so that you're not starting with this being 0, 0, but rather maybe this being 50 and 0, so that we can examine it from 50 up to 100 where stuff is actually happening. So eliminate the useless part. Remember, your x-axis is your independent variable, your y-axis is your dependent variable, and then just scale the graph accordingly. If you have issues doing this, we'll make graphs on Excel. We're going to work with Excel in this unit a lot too, so we'll have plenty of time. You should also be careful to have enough data points to figure out if the relationship is linear or quadratic or what have you, if it's a squared function, an inverse function, and there's 2 different things that we can look at. So what we can see here is that this graph on the right has enough data points to see that there's basically a linear fit. With only 4 data points, I can make a rough assumption that, oh, okay, well, the first 2 are just above the line of best fit. If we're calling this linear line my line of best fit, which is incorrect, I can make a really crude assumption saying that my first point is above the line, my next 2 are below the line, and my fourth one is above it. So it's really a line of best fit with a little bit of random error in there. when in actuality, if we get a fifth or a sixth or a seventh data point, we could see these points going up and up and up, and then we could actually correctly recognize, oh, it's much more like a quadratic function. So be sure to gather enough data points for you to make a reasonable assumption to see if it's a curve or a straight line and how to use it. This is the basics. You're going to have more questions as we go on. I just didn't want to flood you with too much dry information. I will see you all very soon. Thank you.